here. I submitted my abstract as you did, but I was too late to do the registration, and that is why the program was dropping my presentation. But now you see the abstract in the another paper, and I enjoyed being joining the IPCC report, which Axel served. We served together the 5th report of IPCC, and served for the Paleo-Climate chapter. And so I would like to talk about another contribution of climate modeling, but a little bit a short time scale. I love to talk about the ice age cycle, but it's even shorter than the ice age cycle because we now see a lot of abrupt climate changes. So I work with these young people in Tokyo and also in Japan now, all over Japan, and I would like to thank my co-authors. Okay, so now we talk about this millennial scale climate variability that we really learn a lot from the ice core people, as Paleo-Climate people, and Paleo-Oceanographers. It's known for as Danska-Doshka events or Heinrich events, but I will mainly talk about the emergence of Danska-Doshka events today. So it's often seen under glacial periods. As in this lower panel, this is one of the interglacial cycle here, and if we have a close look, it occurs a lot during the middle glacial. It's not so much in the first part, but it has some, and it's not so frequently occurring in the -2, -4, but it's a lot in the -3 and some in the -5. It's not occurring with the equal periodicity. It changes a lot. It changes its intervals, and also it has sometimes a shortening of interstadial lengths. For example, it's known as bond cycle from DO about 13, 12, 1 to 11. 8765, for example, and you will see that the interstadial and stadial lengths are changing. First the longer interstadial, and then the stadial is getting longer and longer. So why are these happening, and how about in the past glacials? For example, I think Kronis is going to talk about the far past before the MPT. And I think this is very important to think about when we talk about the human evolution, which could be influenced by this kind of quick, abrupt changes. So I'm going to use our Japanese model. It's a MIROC. It's called MIROC model, and it's one of the IPCC class model. But I will use earlier version. It's not the latest version because it's always very expensive to use the latest version. But it is the version that was published for the CMIP. And now the resolution is about 2.8 degrees. It's about T42, and it has 20 levels. And for ocean, it's 1 to 1/2 degree, 44 layers. I will first start showing our results in the deglaciation, which includes the DO 1 and 0, known as Bering Araroid and the Younger Dryas. And I will show you some experiments that we have done for different CO2 levels and different orbital situations, and comparing the case with glacial ice sheets and no ice sheets. There are some published results already from other groups, but I hope that I'm covering different parameter range to understand the DOs during the glacial cycle. Okay. So this is first our results of the deglaciation experiments. I'm following the Ivanovic paper that was published as a PMIP4 kind of protocol, and it's now published, led by Obase, our young, he's a researcher. It's covering the starting from the LGM, but going to the near the Holocene, and following the change of the orbital parameters, like the changing obliquity, changing eccentricity and precession, and the CO2 changing, following the protocol. And then also the important is that we have to set the freshwater. Okay, some of the previous studies switched off the freshwater to get the Bering aeroid, because if we reduce the amount of freshwater, that allows the switch to the from stadial to interstadial. But in this case, we try to demonstrate that the switch from stadial to interstadial, or the weak AMOC to strong AMOC, or the very cool Greenland to warm Greenland, could be simulated without changing the meltwater drastically. Okay, so that is the point of this paper. The red line is our model results, and the black lines here are from the observation or Paleo-Climate information. For example, the North Atlantic information, or the Greenland isotopes or Antarctic isotopes. Now, if you look at our results, in the red line, you see that we have the kind of abrupt change in the AMOC here, around the timing of 15 Ka, known as a Bering aeroid, and also an abrupt change of Greenland temperature. The temperature of Antarctica is not abrupt; it's a gradual increase of temperature, and then after this Bering aeroid, it has a gradual decrease, so cooling, as known as the cold reversal in Antarctica. And then this is the mean ocean temperature of our model in red, and the black from the ice core community. The change in this model is as abrupt as the Greenland ice core people show for the northern hemisphere. So I hope that we are capturing some of the characteristics in a lot of Paleo-Climate information. Also, we try to look at the global distribution. I should have maybe made a video for precipitation, but anyway, this is the temperature, and you see that there's the northern hemisphere, southern hemisphere gradually increasing, but a lot in the southern hemisphere. Sorry, maybe I should have started. Okay, yeah, starting from the yeah, and then you see that the Antarctica is gradually warming even before the big change of northern hemisphere, and then also the tropics, low latitude, and also Pacific is also warming, and then finally the northern hemisphere, North Atlantic is warming. So I think it's covering almost the order that we see in Paleo-Climate information. Also, we try to demonstrate that we can show the younger Dryas even without having a drastic flushing of fresh water, with the increase of meltwater, gradual increase, but the gradual increase of CO2 and gradual increase of insolation. So it's a kind of intrinsic oscillation that we think occurring over the gradual change of the background parameters that we know during the deglaciation. Also, we were showing the difference between the penultimate deglaciation and the last deglaciation by showing so now the different color, red and blue, black is the penultimate deglaciation from known as termination 2 in red and termination 1 in black. This is also published in another paper, and we demonstrate that this difference can be seen. One like a HS11 without having a big change like Bering aeroid or younger Dryas in the last deglaciation for the termination too. And the only difference is the freshwater amount, a little bit larger freshwater in a short period because of the large eccentricity. So we think that there is we capture these kind of characteristics as intrinsic oscillation, but depending very much on the background climate. Okay, now I'm going to talk about the dependence on the background climate. But from this slide, I'm going to show a case without changing the background climate, background forcing. For example, this is a case that we did integrated for 6,000 years without changing the CO2 orbital and meltwater, but just showing the intrinsic oscillation in our model. It has the AMOC and Greenland in red, AMOC in black, very abrupt warming and cooling, while the Antarctica temperature is showing a gradual warming, cooling, warming, cooling. Just like the ice core record. Also, this is a comparison to the DO7, which I would like to show that it's the right speed. And also, this is the sea ice. We think that the sea ice cover is very important for switching from stadial to interstadial or interstadial to stadial back, because it interrupts the interaction between the atmosphere and the ocean. When the sea ice covers, it prohibits it prevents the atmosphere cooling the ocean and allows the subsurface ocean to warm gradually. And this is finally gradually influencing the southern hemisphere or the low latitude through the ocean heat transport. Okay, so this is again kind of movie showing the time sequence, a bipolar seesaw, but it's really interesting that the Antarctica is changing, and then gradually low latitude is changing, and then suddenly the North Atlantic is changing. And again, the Antarctic is changing, tropics is changing. So we have to think about the bipolar seesaw, or it's like a global seesaw, I would say. So what is happening in our model is like we have a slow process here on the top and the bottom, and from top to bottom or bottom to top, this is a fast change, abrupt change. So this is 100 years, and then so for example from a very stadial, bottom is a stadial. While it is the stadial, the Antarctica is gradually warming. And then if we look at the ocean, the density is gradually becoming smaller. The density is green density means that it's fresher, or it has a gradual warming compared to this stage. And then abrupt change occurs. After abrupt change, then the northern hemisphere is of course warming abruptly, but then the ocean is starting to cool down because of the transport of the ocean and the brine rejection in the southern hemisphere that would affect the salinity of the bottom of ocean or the deep ocean, and also the cold temperature is densifying the ocean, whole ocean. So the gradual change occurs during the interstadial, and finally that ends up to the fast change of the whole world from interstadial to stadial quickly. So there is a kind of interplay between the northern hemisphere, North Atlantic sea ice, and the southern hemisphere bipolar seesaw. I think this is something that we have to investigate in detail in our model, but now I would show that this kind of abrupt change or this oscillation is sometimes occurring, sometimes not occurring, depending on the CO2. Already there is publication by Klockman and Betterotti or some colleagues in in previous papers, but we show that we also follow that we have a mode that there is no oscillation when we have high CO2. Also with the low CO2 we don't have, it's a very weak AMOC or very low Greenland temperature, and in between in our model between 185 ppm and 240 ppm we have kind of intrinsic oscillation of the AMOC or the Greenland temperature and the gradual change of the Antarctica or the Southern Ocean temperature. So we have this kind of three modes. This oscillation doesn't occur if we apply our interglacial ice sheets, meaning that if there is only Greenland and no North American or European ice sheet, I don't get it in America at least. I just get a little kind of a change at a very low CO2. But anyway, it's very different when we once have a ice sheet. We start to get this kind of oscillation because of the cooling and the windy situation because of the ice sheet. Now, not only with the ice sheet, but there is some influence from the orbital parameters. We change the obliquity. From the right to left, it's the obliquity change, large obliquity to small obliquity. The colored lines are for the precession, same as the LGM or the close to present day, very the cool summer for Northern Hemisphere, and the gray one is for the hot summer in Northern Hemisphere. So there's a change in the precession if you go from gray to color. You see that the kind of sweet spot of the occurrence of this intrinsic oscillation occurs very much depending on the CO2 level and also the obliquity change. Okay, so you start to see the oscillations around here, not with the high obliquity or high CO2 or low CO2 and low obliquity. The precession seems to stretch a little bit the kind of the zone of oscillation or the sweet spot or Goldilocks zone, if you like to say. Okay, now if we look at the real world, if we follow all the DO numbering from 25, 4, 3, 2, 1 to down to DO2, we can. Okay, yeah, we can, and we know from thanks to the Paleo-Climate information, we know the CO2 and the obliquity, and we can make a kind of trajectory. We can follow the trajectory going up and down because of the CO2, also changing millennial scale, but also that is going through the kind of zone that we were showing that the oscillation could occur in this model. And finally, it enters this zone in the beginning, and also with with the long interstadial, the relatively long interstadial, and finally with the longer stadial, depending on the CO2 and obliquity. It's quite complicated, right? This I can show that the length of the interstadial, the duration is quite consistent with the ice core data for different data that they report. And also we can see that we can maybe understand the kind of bond cycle from the ice core data, that it is following quite a lot the obliquity for this time, because the CO2 didn't change so much. It is flat around 200 ppm, but the obliquity was changing a lot through this time. So altogether, the obliquity and CO2 is making this kind of change of the duration of interstadial and stadial. Finally, about the time before MPT, now we are starting to learn a lot from the paleostratigraphy community and maybe from the speleothem community, I hope. For example, the papers showing kind of a millennial scale oscillation, or I don't know if you call it Danska Doshager, but there are a lot of frequent oscillations when the low obliquity is shown. I think it depends very much on the CO2, what the CO2 is. So I'm looking forward to the information that we get from the different communities, from Blue Eyes or the paleoceanographers. But if we take one of the CO2 curves from the Mulder's van der Waal et al. And combine it with the obliquity, we can maybe think about that it could have happened, the kind of oscillation could have happened from around 2.7 or 3, with a little bit touch in the zone of this kind of zone that I showed in our paper, in our model. So now if I summarize my work, I show that there's an unforced oscillation or a kind of intrinsic oscillation as a sweet spot in our model, and it depends on the freshwater or the obliquity, the precession, ice sheet, and CO2, but mainly the CO2 and obliquity for determining the kind of width or the kind of range of sweet spot. And the bond cycle could be a kind of occurrence during the degrees of obliquity, and maybe we could also apply it for the to interpret the millennial scale oscillation before MPT. Thank you very much for your attention.